Okay, so in this video, we are going to talk about more practical numerical ways to solve something like Gauss's law. Um, because in most scenarios, we won't have a nice analytical function that describes the electric field or the charge density. All right, so in real world, we're not going to have this nice function, but we could potentially take an electric field probe and measure the electric field at all different points along the grid. And using that, we can make good approximations and make what's called a numerical solution. And in order to do that, we basically, let's go back to the definition of Gauss's law, right? That the gradient of D equals the charge density, and that equals the differential of the x component of D with respect to x, plus the derivative of the y component with respect to y, and then the same for z. So we basically need a way to approximate this derivative, d x component with respect to x, even if we don't have measurements at every single point in time, and nor can we fit a function to it. So let's talk about how we might do that. And let's start out with one dimension, then we're going to expand to 2D and 3D from there. Right? So let's say everything is along a line. Right? The whole world is a single line. And what we can do is we can walk through and we can measure the D field everywhere along this line. And the D field is also constrained to be in one dimension as well, right? This is a one-dimensional world. And let's say we make measurements that look like this, right? So this by the way, is the x direction only. Let's say we make measurements like this, 5.1 and 5.3, and then 4.9, and then 5.0, right? And it's starting to change, 5.6 and 5.9, maybe 6.2, and then 5.9, right? It's changing a little bit. And so from this, we can sort of, reproduce what's happening. Clearly it's going up, it's going down, back up again, and then it kind of starts to fall. So we've got this function, and we're basically able to approximate this function pretty well with a series of discrete measurements that are separated by a distance of delta x. Right? Now, if we are basically sampling this function or measuring it with a good enough density, then we can reproduce the variations pretty well. If delta x were really big, like this, then this wouldn't work so well, right? I take a measurement here, I take a measurement there, I take a measurement here, and I wouldn't do so well, right? I got a measurement here, here, and there, and now all of a sudden my approximation is not so good, right? I don't have a very good reproduction of that shape. And so if you've got a dense enough measurement, then we can sort of approximate things. But how do we do it, right? We want to know basically the derivative of d with respect to x, right? So let's look right here. If you can take the derivative, right, you can look at the slope of this line, but the next best thing is to look at this point and that point and take the difference. In other words, the derivative of d in the x direction with respect to x is approximately equal to 5.9 minus 5.6 divided by this delta x, right? This is basically the definition of a derivative, except we take away the limit, right? The definition of dx dx is dx at x plus delta x over 2 minus dx evaluated at x minus delta x over 2 divided by delta x, and then we have to have the limits as delta x goes to 0. Kind of squash this a little bit. Let me rewrite that. Now, this is our definition of the derivative of dx with respect to x. Right? So if we take this same thing and we just get rid of the limit and we just say, make sure delta x is small enough, then what we're really doing is we're taking the differences of adjacent points and divide it by the separation of those points. And that's what we're doing right here, right? We can approximate the derivative as being the difference of two adjacent points divided by delta x. That can be thought of as the derivative d dx evaluated at the midpoint between them, right? So in order to figure out what the derivative is at this green line, we're going to measure the d field on either side of it and take the difference. And that's going to be a pretty good approximation of what the derivative is, as long as our measurements are sort of tight enough in spacing. All right. So that's in one dimension. But let's talk a little bit about how we might extend this into two dimensions, because there's a bit of a complication that comes up, right? So now we're going into two dimensions. And to do that, I'm going to draw a little matrix of points, or a two-dimensional grid. I'm going to try to draw 16 points. My drawing here will be so-so. You can take a look at the notes where I've done this probably a little bit better. And I'm going to label these points as D14. No, that's too small. D14. This is D13, D12, and D11. I'm going to keep adding this around. All right, and this is A, 2, 4. Sorry, not A, it's a D right there. All right, this is D24. So I'm just basically, defining the measurement that we might make in each of these so that we can set up the approximation. All right, not A. Okay, A23. D33. Let me just write down all the D's first, so I don't make that same mistake. D33, 4-3, almost done here. This is 2-2, 3-2, and 4-2. Okay, finally. All right, so now we've got two different differential distances. We've got a delta x, and we've got a delta y. Right, a separation of the cells in the x direction and the y direction. In practice, they don't have to be the same, but they very often could be in a practical system. And so now we're going to approximate that the divergence of d is the derivative of the x component with respect to x plus the derivative of the y component with respect to y. All right. So let's try to approximate this. I'm going to draw a red dot right here because we can approximate d dx dx right here. We can say that the derivative of dx with respect to x is approximately equal to d24 minus d14 divided by delta x, right? It's the difference of the two adjacent cells divided by the delta x. All right, we can do the same thing for this point down here. For this point, we can say that the derivative of the x component with respect to x is approximately equal to d23 minus d13 divided by delta x. All right. Now, what we really want to know is the partial derivative or the divergence here at this corner right here, where all four of those cells merge. And so these two red dots are offset in both directions. And so to basically take the two red dots and figure out what the value is at the green, we can just average the two. Right? So d dx dx evaluated at this green point will simply be the average of these two things, right? So it's going to be the average of this plugged in here plus the second one plugged in right here, right? And that's basically, we're effectively interpolating. right? We've got a measurement of the x ddx dx at this red dot, another one at this red dot, and we're just going halfway in between to figure out what it is at the green dot. We're going to repeat the same process for the y component, right? For d, dy, dy, which we can define at this blue dot, we can define at that blue dot, right? So d, dy, dy will equal to the average of the two values from each of these two locations, one from here and one from there. Add those up and divide it by 2 since we're taking the average, in which case our approximate divergence will just be the sum of these two, right? We've got an approximation for ddx dx, and we got an approximation for ddy dy, and that's going to equal right here. This will come here, and this one will roll around there. And now we got a pretty good approximation for our divergence of D, right? So that's a two-dimensional way to do this. And you see it got a little bit trickier because we have to do this averaging in order to interpolate the points. And that's just kind of pops out of 2D geometry. Let me kind of show you this pictorially in the notes. All right, so think of this as there essentially being 4 one-dimensional derivatives. So this plot right here, we want to calculate what the divergence is at the green dots. And we've got basically our vector field, in this case I wrote it as A, defined in each of these 4 points that are surrounding it, right? To the northeast, to the northwest, to the southeast, and to the southwest. And each of these 4, we've got our vector field defined. Right, and so the vector field is basically x0, right? And this point right here is at the location x0 and y0, in which case this point right here is x0 minus a half of a grid cell, since this length right here is delta x over 2. And it's in the positive direction from the center by y over 2, since this length right here is delta y over 2. All right, so we basically have 4 different measurements offset in 4 different diagonal directions from our center point. And we can basically come up with 4 one-dimensional derivatives, 2 of them for day, dy, which are the 2 blue dots, right? So this blue dot is basically the sum of the red dot above it and the red dot above it divided by 2. So the left blue dot and the right blue dot. The right blue dot is basically defined here, right? It's the difference between this point above it and this point below it, and the fields that are defined in each of these locations, divided by delta y. And we're going to do the same thing with the red dots as well, except for the red dots, we're averaging the side-to-side variations, the one that's to the left and the one that's to the right. And to take the combination of these red dots and blue dots, we're going to take the average of everything. So average the 2 blue dots, and that's going to give us our best guess of day, dy. Take the average of the 2 red dots, and that's going to give us the estimate of dax dx. Everything is now calculated at the green dot location and sort of centered nicely. And then the total approximation for the divergence of A is just going to be the sum of these 2, right? Day, dy plus dax dx. And so now we can approximate everything in 2 dimensions. All right. So this gets a little more complicated, but I at least want to show it to you so you can see that you can repeat the same exact process for 3 dimensions. Again, it gets just another step of complication, but for that to work, you need to average 4 pairs of one-dimensional divergences to get the 3D divergence. Since from a single point in the XY plane, I can go in 4 different directions. So I got to average all 4 of those to get the value, or estimated value for one of those derivatives at the center point of the cube. Right, so in this case, we're defining divergence at the corners of the voxels, which is the point that's kind of inside the center of this cube that you can't quite see. But we're using all the measurements at the center of each one of those cubes in order to calculate that. So I do have that written here in the notes in case you want to take a look at it. I'm not expecting you to know this and calculate it, but at least be aware of it. So the approximation for the derivative dAx dx, first of all, we're going to have an average of 4 different pieces to it, right? And each of those 4 rows is basically a one-dimensional derivative, right? It's a difference of 2 points that are separated in the x direction from each other, right? So in this first row, notice that the x-coordinate on the left and the x-coordinate on the right are off by exactly 1 delta x from each other, whereas the y component is the same and the z component is the same. So these 2 points left and right are displaced by exactly 1 delta x from each other. And the same is the true for the second, third, and fourth row. And then we're summing up all 4 of those and taking the average with that 1/4 right there. And the delta x is again just that delta x separation between the 2 points. All right. And so there's the average right there. You can repeat this same process for dAy dy, dAz dz, and then you can make a 3-dimensional approximation as well. So in practice, this is the way problems like this are solved, because you cannot solve these things analytically. You often need to have numerical solutions based on either measurements or based on simulations. And this is sort of a simple but powerful way to do that in reality. And so we're going to move on from this lecture, and we're going to start to see other ways in which we might relate electric fields, other quantities. In particular, we're going to now introduce something called gradient and voltage based on our understanding of electric fields and charges.